Then we introduced another way to quantize our theory, which is based on canonical quantization, and in that case we impose commutation relationship at equal time when we deal with bosons and anticommutators when we deal with fermions. And if we don't do that, we end up with a theory which has no ground state for the fermions, at least for free spin 1/2 fermions, and that is a link with spin statistic connection we saw earlier, and in particular that justifies the existence of the Pauli exclusion principle. We also use canonical quantization to show that causality is preserved in quantum field theory. We then looked at the possibility to form systems of particles which interact with each other, and that's possible at low energy. In this case, an important object is a propagator for one particle. So that describes the propagation of a particle surrounded by these other particles, where all these interactions occur. We saw that this propagator obeys Dyson equation, so that's an exact equation, and which can be solved approximatively when we use a mean field approximation. And in this case, we end up with a set of single particle Schrödinger-like equation with a mean field describing the average interaction of each particle with their surrounding particle. So that's a self-consistent equation which depends, where the mean field depends on the density of the system. We then studied superfluidity, which can occur, for instance, in cold bosons. So we started with Lagrangian for scalar fields, and because we want a finite number of particles, we introduced a chemical potential, and that produces spontaneous symmetry breaking. And as a result, we have a Goldstone mode at low energy, which is corresponds to our superfluid system, and that led in particular to the dispersion relation. So what is the relationship between the energy and the momentum? And in this case, instead of a quadratic dispersion relation, which we would expect for non-relativistic system, so E proportional to P squared, we ended up with E proportional to P. And as a result, the level density is much smaller than what we would have for a quadratic expression. And that explains why the superfluid cannot dissipate, because with a small level density, there is a smaller probability for the excitations to occur, simply because there is less available states. And if no excitation means no dissipation, means no friction, means superfluid. We also saw that the phase is a conjugate of the density, and that's an important relationship for condensed matter. And we saw that the velocity can be expressed as a gradient of the phase in the superfluid, at least in the Goldstone mode, and that leads to vortices when we try to rotate the superfluid. Finally, we looked at superconductivity in metals, so that when we have formation of Cooper pairs, so two electrons couple each other into forming a boson, or something which behaves like a boson. So we could write Lagrangian for a scalar field, but this time with imposing local gauge invariance. And we saw that if we have local gauge spontaneous symmetry breaking, then we have a Higgs mechanism, and that can explain superconductivity. So what happens is, below some temperature, the system becomes superconductor, and it repels the magnetic field. So there is no magnetic field inside the superconductor, and that's how you can explain Meissner effect.